So let me just thank the organizers for accommodating all our needs, because we came with our daughter, and I don't know if she causes any trouble to you, well, sorry. All right, so I will talk about weighted distances in scale-free random graph models. And to start with some motivation, or where is this coming from, I will give some examples of information diffusion, which means just basically any type of spreading process on a graph. So you can think of viruses, for instance, they spread across the society. So here you can see the spread of the Zika virus all across the world, starting from Africa. And then here you might have heard of a completely different virus, a ransomware attack called WannaCry, which affected, I think, computers in May 2017, and it basically spread across Europe in 3 days and caused a lot of trouble. So these are sort of emblematic examples of information spreading on some networks. Here it is the internet network. But you can also think of other more fun things like the spreading of memes on online social media. This Visa Packer meme spread in a couple of days all over Facebook. I'm sure you have seen it or some versions of it. Of course, you can think of viral videos like the Gangnam Style, which hit 1 billion views just in a couple of months, right? So the goal of a part of my research is to understand and describe mathematically how these type of processes spread on networks. And to be able to do so, we need models. So, and to be able to model information spread on real networks somewhat realistically, we need to first do some analysis on these real-life networks to be able to find the model that fits them, sort of at least. And so the first observation is that many real-life networks have power law degrees. So this means that the number of neighbors of a vertex in the network follows a power law. So the probability that if you pick a vertex uniformly at random from your network, that the degree of that vertex equals x, decays as a power of x. This power is typically, or I will denote it by tau, and the way physics papers show this is by plotting the log proportion of vertices with degree x against log x, and then you should see a straight line with slope tau. So this was first observed, or one of the first observations of this phenomenon was by Falosus and Falosus in 1999. No, I think 3 brothers, or I'm not sure about the precise relation. But anyway, so they plotted the degrees of the IP level or router level internet network as it was growing from November 97 to March 98 and December 98. And this is IP level, and this one is router level. And they found that even as the graph grows, the model follows a power law, with the tau being sort of minus 2.2. Okay? And then here's another completely different example. So in the literature, if you open up any real-life network literature, you can find examples: protein interaction networks, gene regulatory networks. Many of them follows power laws or truncated power laws, but not everything is a power law, okay? So you have to be a bit careful. So these are ecological networks where there are animals and plants, and they are two of them are connected if the animal pollinates the plants or eats the plant in this case. And you can see that some part of the network, it's a bipartite graph in this case, follows a power law while others don't. So it's not always a power law, but many of them are. So another important observation that will be relevant in my research, that the power law parameter, so the exponent tau, is very often between 2 and 3. And this will be crucial. So this does make a difference. Why? Because in this case, the empirical variance of the network diverges as the number of vertices grows, okay? While the average degree stays bounded, okay? So this sort of makes a big difference in how processes behave on the network. All right, so one of the easiest models that you can fit to such degrees is called the configuration model. So for those of you who haven't heard of it, it's just a model that matches the degrees of the network. So if you have a network with a given degree distribution or a given, how do I click with this mouse? Oh, I guess on the side. Man, can someone explain me how to use the mouse? No. I have no idea. Okay. Yeah. Okay, now I completely lost it, it seems like.
You broke it.
Yeah. Oh, yay. I'm sorry. And this one, maybe? Okay. Now it works. Okay, and then I wanted to click on, let's say, this link, the first one, and then later the second one. Okay, so what you see is for each vertex, you plot a little half edge, and how many half edges you plot there is going to be the degree of that vertex. And once you did this for all of the vertices, you just take a uniform matching of all the half edges. So a uniformly random matching. This gives you a graph. And the randomness sort of comes from the matching, right? So this is the end result. All right. Now, it's not, you can still click, or explain me how to click.
You just click.
Like this?
Yeah.
Okay, so where is my presentation? Sorry, I'm like technically challenged, it seems like.
No, it's not very good.
Okay.
Okay.
Okay, and now the second one. All right, great.
You drag it?
No, I want to just change the power law over there. Okay, so if I change the power law, so let's say 2.7 and the number of vertices to 1,000, then you get a network like this. So this is sort of what I'm having in mind. So the power law exponent is somewhere around, between 2 and 3, and the number of vertices is large. And as you can see, there's like a core, right, where there are high degree vertices in the network because of the power law relationship. And these high degree vertices are sort of clustered in the middle. So this is the graph I would like to understand. And if I increase this to, let's say, 3,5. No, this is minimal degree 2. But minimal degree 2 helps us because then, there's basically one connected component. Okay, so this is when tau is above 3. And in this case, at least in the limit, there's no core. Okay, so as tau crosses from 2 point something to 3 point something, the core disappears. So it more becomes like a web. And yeah, so this is sort of the difference between tau between 2 and 3 and tau above 3. So now, can you help me find my presentation? I can proceed. Great. Yay. Okay, so once we have this graph, so this is what you have in mind, this graph with the very high degree vertices forming a core. To be able to model the information diffusion, we just add i.i.d. edge weights to each existing edge, and we think of this as the transmission time of the information through that edge. Okay? So if the information reaches one vertex, it takes that edge weight amount of time to reach the vertex next to it, along the edge. Okay? So in this model, the spreading time from one vertex to the other, so if the information starts at some vertex u, the time that it takes to reach vertex v is just the weighted distance in this weighted graph. Okay? So this is a random object for two different reasons. Well, the graph is random, but also the edge weights are completely i.i.d. Okay? And so the question is, how does this distance behave in terms of the degree distribution and in terms of the edge weight distribution? So we would like to characterize the university classes of this object. Okay? So to be able to do so, the first thing you should be able to do is to understand the graph locally. How does the graph look from the point of view of, let's say, the initial vertex of the spreading? And it is common, or it is kind of well known, that the configuration model locally, in the local V-convergence sense, converges to a branching process. Okay? And because of the way the model is defined, you are more, the degree of your neighbor, so if this is your original vertex, the degree of your neighbor is the size bias distribution of the original degree distribution, okay? So the local neighborhood of a vertex looks like a random tree with the size bias distribution. So if we want to understand how distances behave, or how this weighted distance behaves, the initial process of the initial part of the information diffusion looks like a random tree where the degrees are power law, and the tail exponents shifts by 1 because of the size biasing. So it's tau minus 2, which is between 0 and 1. So by tail exponent, I mean the probability that the degree is larger than x is constant over x to the alpha. Okay? And then each edge additionally has an i.i.d. edge weight, which is this edge weight distribution. So this is called an age-dependent branching process. Okay? So let me define it to you. So I will denote it by BP x comma sigma, where x denotes the offspring distribution. So the root is just born at time 0. It produces a random variable x number of offspring, and then each of those children are born some sigma time later, and these sigmas are i.i.d. Okay? So this one is born sigma 1 time later, this is sigma 2 time later, so it's born at this moment, and so on. And given that the child is born, it just reproduces completely independently. So it has, again, an i.i.d. number of children from distribution sigma, and all of the birth times are, again, i.i.d., sorry, of distribution x, and all of the birth times are i.i.d. sigma. Okay? So the important important parameter or object to study is the number of born individuals before some time t. So let's say dt is, in this case, so the number of born individuals before time t, in this case is 11, because 1, 2, 3, 4, 5, 6, 7, 8, 9, I guess I missed something, so it should be 11 points before this vertical line. All right. So this is the population born by time t, and the definition that an age-dependent branching process is called explosive if there is some time t such that this random variable, the size of dt, is infinite with positive probability. Okay, so the question is, how can this even happen? Well, if the expected number of offspring is finite, it cannot happen. But we are in the setting where the expected number of offspring is infinite, okay? So in that case, it can happen. And if this happens, the branching process is called explosive. Otherwise, it's called conservative. So this definition goes back to even the Harris book, treats a sufficient and necessary condition for a branching process to be explosive if the birth times are exponential. But here we are having a completely general birth time distribution. So sigma, the edge length, is completely general distribution, not even absolutely continuous, nothing. All right, so the main question is, when is a branching process explosive? And then there was a lot of work on this in the Russian literature in the 80s, and they gave a lot of sufficient conditions, but the necessary condition came from Amini, Devroy, Griffith, and Over in 2012, I think, in an analysis of probability paper. And so I will just sort of have a rewritten version of what they did. So if you assume that the tail of the offspring distribution is at least a power law, so it's 1 over x to 1 minus something, so you have to be like strictly bounded from below by a power law, but you are not very heavy, so it's less than 1 over x to the epsilon. So the tail is not 1 over log x, okay? Those cases are excluded. Then the branching process is explosive if and only if this integral diverges, okay? So what is this integral? Well, you take the distribution function of your edge weight distribution, invert it in the generalized inverse sense, and then you look at e to the minus e to the z dz, and integrate that. You can integrate it from 1 actually, and if that diverges, you are explosive, otherwise you are conservative. So this is sort of a mysterious criterion, but I will explain it well in a second. So, but before I do that, so let's just note that this integral doesn't depend at all on the very precise power law tail of x. Okay, so it only requires that it's sort of bounded from below by some power law with tail exponent that is strictly less than 1 and the tail exponent that is strictly like larger than 0, and this is it. So which means that if a distribution sigma forms an explosive branching process with some power law, then it forms an explosive branching process for all power laws, okay? So in particular for all power laws where the original tau was between 2 and 3. So this criterion sort of comes from the fact that if here's the root and you plot the branching process like this, and zk is the number of the size of generation k, then zk, well, is approximately exponential, well, 1 over well, the tail exponent, so let's call that alpha to the power k. So if you look at the minimal edge length leading to generation 1, and then the minimum edge length leading to generation 2, and so on, so the typical order of magnitude of that is f sigma inverse at, well, 1 over zk. So 1 over the exponent 1 over alpha to the k. So this is the typical order of magnitude of the minimal edge length leading to some generation. And if you sum this up from k, from 1 to infinity, if this diverges, then you cannot explode, of course, because then even the minimal edge lengths are not summable, and any array, infinite line of descent leading to infinity is, of course, longer than that. And what they showed that this criterion is actually sufficient as well. So if the sum of these typical minimums is finite, then actually you can find one ray leading to infinity with finite total length. All right. Okay, so just to give you an example, what distributions are explosive? What are these sigmas? Well, so what matters is how the distribution starts off at the origin. If it's kind of steep at the origin, you are exploding, otherwise you're not. So exponential, gamma, uniform are all explosive. You can just plug this in. This is basically, for exponential, it's just e to the minus e to the z, which is integrable. So those are all explosive. Anything that starts off as a polynomial is explosive. So if you make it thinner, like x minus 1 over t to the beta, that's also explosive. So how thin you can make it? Well, sort of this has to be like this expression has to be like 1 over z, or 1 over z to some power. So you can calculate the boundary case, which is like double exponentially thin around the origin. So e to the minus e to the 1 over t to the beta around the origin, which is explosive when beta is less than 1, otherwise conservative. All right, so let's go back to the configuration model. So now we know now we know that there's a dichotomy in terms of how the information process starts, right? So it either starts in an explosive way, in the local weak limit sense, or not. So here's the first theorem that we had with Remco and the PhD student Enrico Baroni. So if you consider the configuration model with power law degree distribution, exponent between tau between 2 and 3, you add i.i.d edge weights to it from distribution sigma, and if this underlying branching process, so the size bias degrees form the offspring distribution and sigma forms the birth times, if this branching process is explosive, then typical distances, so the distance between two uniformly chosen vertices, tends to just the sum of two random variables. So it converges in distribution, and this distribution is the same as the distribution of the explosion times of two independent branching processes. So what is the explosion time of the branching process? Well, it's the first time that you find infinitely many individuals in it. Okay? So this is nice. Otherwise, typical distances tend to infinity. And for the longest time, we did not know what is this other case. So how fast do they tend to infinity if it's not explosive? And the reason for that is somehow that the branching process part is not very well understood. How does a non-explosive branching process behave? Okay, so let me just mention that this result was first shown by Shankar Bhamidi, Remco, and Gerhard Hochimstra for exponential edge weights. Okay? And then with Enrico, we generalized it to all explosive edge weights. All right. Okay. So this year with the master student Erwin Adrians, we sort of did the missing case. So you assume again that the degree distribution falls in this power law range at i.i.d edge weights. And then if the branching process is conservative, so there's no epsilon there. It's just convergence in probability. So there's a weird expression coming. So is this one. So if you divide the typical distance by this quantity, it converges in probability to 1. So this is the main order of magnitude. So let me explain. So the sum goes to log n over log tau minus 2. Some of you might know that this is the graph distance. So 2 times this is the graph distance. So what you do is you sum up from 1 to half of the graph distance to, well, sort of the typical minimum edge length in generation K. So suppose there would be a branching process approximation, which there isn't this long, but then here you would have a tau minus 2, and if you just sum up the minimum edge lengths in each generation, then this is what you get, and you have to sum it up sort of half of the graph distance and take twice, because from each vertex you go, from U and V, you go half of the graph distance. That takes this much time, and then you somehow connect. All right, but this is the intuition. Okay, so just to have a bit of an outlook, what happens when tau is larger than 3? So what happens when the empirical variance converges? I mean, it's finite in the limit. So this was solved by Shankar, Bamidi, Remco again, and Herald Hochimstra. Correct me if I'm wrong with this result. So if sigma has a density, then what they showed is that the order of magnitude is always logarithmic with a very deterministic constant prefactor, which is 1 over the Malthusian parameter of this branching process. And there's, well, a tight number random variable, which is even converging. I guess if it has a density, then it's converging, right? And if it's not, it doesn't have a density, it's still tight.
You didn't show that.
Oh, you didn't show it, but it's kind of true, right?
Yeah, you believe it.
Okay, so if it has a density, then this tight here converges to a very specific random variable. Otherwise, I believe it's tight, but apparently they didn't show it. Okay, and the reason for that in that case, this branching process is Malthusian, so it grows exponentially. So it takes like 1 over Malthusian parameter times log n time to swallow the whole graph, so to speak. All right. So before I move on to the proofs, let me just tell you, because there are so many spatial people here. So we managed to sort of generalize this result, or actually this was probably earlier, to a spatial model. So this is called scale-free percolation. And before I define it to you, let me just show you a simulation. So this is how it looks like. So it's a power law degree distribution graph on the whole of ZD, okay? Where, yeah, so vertices have power law degrees, but the model is defined on ZD, and there are long-range connections. So how is the model defined? Well, the vertex set is ZD, and each vertex has a vertex weight that sort of describes its fitness. And then, so we added nearest neighbor edges, which are actually not present in the simulation, but just for convenience. And then if you condition on the whole collection of the vertex weights, then 2 edges, an edge between 2 vertices is open with the probability that a Poisson random variable is larger than 1, and the parameter of this Poisson random variable is, well, the factor of the 2 fitnesses divided by the Euclidean distance to some power alpha. And then you have a lambda prefactor, which sort of is a percolation parameter. Okay, so this has a couple parameters. So it has the power laws of the edge of the vertex weights. Then it has a parameter alpha that is like the long range parameter, and the percolation parameter lambda. And after all this, you still add i.i.d. edge weight sigma to the whole model. Okay? So this model was defined by Remco and Mia Deifen, and what they showed, well, they showed among others that the degree distribution follows a power law again with a different exponent gamma that is, well, the combination of the long range parameter, the dimension, and the power law parameter of the vertex weight. So it's alpha times tau minus 1 over d. All right, if alpha is larger than d. Okay, so again, this is the model that you have to have in mind. And what we did is, so if this power law exponent is between 1 and 2, so here there's no real size biasing, so that's why it's 1 and 2. Oh no, sorry, this is the tail, so there is size biasing. Okay, so if this gamma is between 1 and 2, and then you fix a unit vector E, and you look at the vertices at m times that unit vector, then the typical distance, the distance of that vertex and the origin is, well, behaves as a similar formula, so it converges in probability if you divide by a very similar formula. And this formula is, well, you have to go to log m over log gamma minus 1, which is sort of the graph distance, half of it, and then this inverse of the sigma distribution. So, so sort of the configuration model is universal in the case, in the conservative cases at least. Okay. All right. So I will move on to the proofs. Okay. So first I will give a picture proof of the explosion, and I made this picture when I broke my shoulder, so it's going to be very ugly handwriting. Okay, so you do the branching process approximation from both vertices, right? So U and W here are uniformly chosen vertices, and you can approximate with the branching process until you reach, let's say, n to some small number of vertices, so some small power, n to the epsilon. So you can show that these clusters are still with high probability disjoint, okay, so they don't overlap. And as a result, the typical distance has to be larger than, you know, the time it takes to swallow up this branching process here and this branching process there. So since the number of vertices tends to infinity, these converge in distribution to the explosion time, sort of by definition. Because the definition is of the explosion time is, you know, the time it takes to reach infinitely many individuals, which is the limit of the time it takes to swallow up, let's say, n individuals. Okay, so this gives you the lower bound. What gives you the upper bound? Well, we use percolation, so we percolate the whole graph. We use the edge weights as an auxiliary variables to determine which edge to keep. So we keep an edge if and only if its sigma on the edge is less than some epsilon. This is a different epsilon than that one. Okay, so in this percolated graph, every edge has length less than epsilon. And then we can show that the maximum degree vertex, or at least one vertex, in this branching process has sort of high enough degree. And then also that in this percolated graph, this core structure that I showed you on the simulation persists. So there is this core structure. What does that mean? That the core can be decomposed into layers or shells, like an onion, and it has the property that if you are in one shell, if you are a vertex in a shell, then with high probability, you will find a neighboring vertex in one shell, well, one more in, okay? Which means that you can build a path using this recursively to the very, very core. And the very, very core is, let's say, vertices above degree square root of n, and they form a complete graph. So they are connected. Now, of course, this path is in the percolated graph, so it uses edges that have length less than epsilon. And how many layers I have? Well, only a constant number. Okay, so ultimately the typical distance is less than, well, the time to swallow up the two branching processes on both sides plus a constant times epsilon. So you can play this for every epsilon, which means which sort of finishes the proof. Okay. Yes? Sorry? No, the constant doesn't depend on epsilon. It's absolutely epsilon independent constant. I mean, that's kind of the magic about it. Okay, so what do we do for the conservative edge weights? Well, sort of similar. So the picture will be very similar to this, except these branching process parts are going to be tiny. So I don't want to run them to n to the epsilon. I just want to run to some small generation number. So I run them until generation mn, which I will determine later. So I will draw a picture along. So here's U, and this time I do really a generation branching process. So this is generation mn. Here's, let's say, W, and it has, this is its mnth generation. And then I do a percolation again, but it's a bit more tricky this time. So I say I keep an edge if and only if its edge length is less than some threshold function that depends on the degrees of the vertices that the edge connects. Okay? So if the edge is between a vertex of degree 100 and 300, then this threshold function depends on these degrees. And the higher the degree, the smaller this threshold will be, which sort of captures the idea that if a vertex has very high degree, its minimal edge length is very tiny. That goes out of it. Okay. So after this, so I will talk about this in a second, a bit later, how to choose this one. But then I also want to find in these branching processes, in the last generation, a vertex U tilde, and here a vertex W. So this is, let's call this V tilde. And what I want is that the percolated degree of it, so dag P of U tilde, is larger than some Kn. Okay? And this Kn will depend on the Mn. So I want this to be fairly high, at least tending to infinity. All right. So let's talk a bit about how to do this degree-dependent percolation. So there's an argument of Jansson that says that if you do percolation on the configuration model and the probability of keeping an edge factorizes into, well, two parts, a function of the degree on the two sides, then you can look at the resulting percolated graph as a new configuration model. So maybe in Jansson's paper you cannot find precisely this version, but we did it with, well, it's sort of hidden there, but we did it with Enrico very precisely, so you can find it in one of our papers. And so the reason for this is that somehow you can reverse. So the configuration model, let me remind you, is that you drew these half edges to the vertices, and then which was the degree, and then you just took a uniform matching. So instead of first matching the half edges and then doing the percolation, you can reverse the order, and if the percolation probability factorizes, and just kill or keep every half edge with probability P. If this vertex has degree d1, then you keep this half edge with probability P d1, independently of everything else. And here this is d2. You keep each half edge with probability P d2. And whichever you didn't keep, sort of this half edge, you move it out. So you don't erase it, but you detach it and move it out. And then maybe this one you also didn't keep, so you move it out to an artificial vertex of degree 1. And then after you have done this, so maybe this one is kept, this one is also kept. After you have done this, you match all the half edges, and you just look at the subgraph that is formed by the kept half edges. And that subgraph has the precise same distribution as as the percolated graph. So it's a tricky argument. All right. So I will choose this. So we are free to choose this p function that depends on the degrees. And if I go back, so in this one, it was just a constant, right? So you kept every edge if its edge length was less than epsilon. So that means you keep every edge with a constant probability, which of course factorizes. But here I have to choose the PD, and I choose it stretched exponentially in the log degree. So I take some eta that is less than 1, and this is my PD. And then, so what is the threshold function coming from this PD? Well, you just have to apply the expectation on both sides of here, and they have to match. So what you get, that your threshold function is the inverse of sigma, of the sigma distribution function at this place, which is PD1 times PD2. Okay? So why this? Why I chose this function? Well, because if eta is less than 1, C is arbitrary, then it's power law preserving. So if the original distribution follow the power law with a certain power law exponent, then the percolated degree distribution still follows the same power law. I mean, the power law with the exact same exponent. Okay? So somehow it doesn't destroy the structure. If the percolated, the probability of keeping, well, a half edge is this formula. All right. And this is basically the best you can do. If PD is much smaller than this, you lose the power law. All right, let's continue. So let's put it together. So because of this Janssen's argument that the percolated graph is still a configuration model, and because we chose the percolation probabilities so that it's power law preserving, so you again have the percolated graph is a configuration model with the same power law, so you can find again this layering structure in it. Okay, so just like before. The only difference is that now you start at a degree that is much, much smaller, some kn. So the next layer has degrees kn to the 1 over tau minus 2. The second next layer has kn to the 1 over tau minus 2 squared, and so on. These are increasing, and you can go up all the way to degrees that are larger than square root of n. All right, so if we put this together, so there's a path here that you constructed this way. So what is an upper bound on the length of this path? Well, you have to go from u to, oh sorry, this should be sigma here, not L. So you have to go from u to u tilde within the branching process, and from v to v tilde, and then an upper bound is, of course, the threshold functions, right? And that's just the threshold function on these degrees. Okay, so let's put it together. So this is just copied from there, and this is my threshold function, f sigma inverse, the log degrees to the power eta. So these are your degrees. So you can just plug them in and see what comes out. And what comes out is, well, you have to like transform the sum to an integral, change variables, transform it back to a sum, and what you get is this one. So you get a factor 1 over eta in front, and then the sum only goes to eta log n over log tau minus 2, but other than that is basically what we want. So f sigma inverse at e to the 1 over tau minus 2 to the I. So this is what we want, except I don't want here this eta, and I don't want here this eta. Okay, so how to choose eta? So eta is less than 1, so the summation boundary is just fine if I drop the eta. So that's again an upper bound, but this is bothering. So I have to choose the eta let's say, less than, so that 1 over eta is less than 1 over epsilon over 3. Okay? And then this is with high probability. This holds with high probability. So now what I have is that the distance between u and v is less than dl. So the time from go to here, from here to there, and from here to there, and plus basically what I want. Okay? So I have to deal with the first two terms still. So I have to show that I can choose an Mn so that these terms are negligible. But Mn has to tend to infinity, because if this Kn doesn't tend to infinity, then I lose the convergence in probability. Okay? So the way to do that is you choose this u tilde based upon the degrees it's only, and not looking at the edge lengths or edge weights. And then you can use that this vertex is in generation Mn. So the time to go from u to u tilde is just dominated by, well, the sum of Mn i.i.d sigmas. Okay? So what we have to show that the probability that this expression is, let's say, larger than epsilon over 3 times what I want is negligible in the limit. And I want Mn to tend to infinity. So this is not so trivial, because sigma can have extremely heavy tails, like 1 over log n, but we showed that regardless of the tail of sigma, you can do that. So there's actually, generally, it's true that if you have a sequence an that tends to infinity, and the distribution, let's say sigma, then there's always a z of an that sigma I is larger than an. So this tends to infinity. So there's always a choice of z, a sequence. Sorry? Oh, to tend to 0, yeah. So for all an tending to infinity and for all distribution sigma, there's a z of an that tends to infinity, then that you can do this. And somehow this z depends on, of course, it depends on an, but also very heavily on the tail of the sigma. So if it's finite mean, you can just use Markov's inequality and choose one, but if it's infinite mean, then you have to work a bit harder.
You want the limit to be 0, right?
Yes, this should be 0. So if it's the other way around, then you are 0. Then it's 1. Okay, so let's combine. So I have here 2 times 1 plus epsilon over 3 times this, and these are at most epsilon over 3 times that with high probability. So if you sum them up, then you precisely get, well, what we want, which is, let me go back. No. Here, there's a. So then you precisely get that this sigma uv is less than 2 times 1 plus epsilon times this expression. So we get the upper bound like this. Okay? So this finishes the proof of the upper bound, which is the harder direction. So I didn't put it on the slides, but the lower bound is fairly simple. Because I still have time. So what you can do is, so here's u, and then here's some generation, I don't know, kappa n of u, and here's v, and some generation kappa n of v, and you can show that you can couple the local neighborhood of u and v to the branching processes all the way until generation kappa nu and kappa nv, so that these two tend to infinity with high probability, and these are still disjoint. And then you just do the Amini-de-Vrooy-Over trick that, so this sigma u and let's say the last generation is larger than the sum of the minimum edge lengths leading to each generation, okay? And so this is the sum of the minimum to go from, so the sigma distance between generation k to generation k plus 1. K goes from 0 to kappa n, let's say u minus 1. And then you just, you just use how big these generation sizes are. They are approximately this. You plug that in. You know that the typical minimum behaves like this, so you get the lower bound.
But wouldn't you need kappa n to be a whole log log n?
Oh yes, yes, of course. I mean, if it doesn't tend to infinity, then I mean, if it's less than log log n, then you have a problem. So this is, let's say, log log n over log tau minus 2 plus i.i.d. And then you are good. Because you only lost a bit. Okay. All right, so maybe I stop here. So thank you for the attention.